Hi friends, good to see you after a long time. So we have made a lot of progress on our course on helicopter dynamics. Today I'm going through lecture 65 in this course, and essentially today we are going to look at lag bending, and then we are going to look at the FEM model for this lag bending and how it differs from the flap bending model. I am Dr. Ranjan Ganguly. Now, if we look at the equation for lag bending, we will see that there is a similarity between this equation and the equation for the rotating flap bending blade. Now, the difference is in the fact that you have this extra term here, which is the vertical component of the centrifugal force. So just to recapitulate, you have the bending term here, the flexural bending term, where EIZ is the lag stiffness. You have the term due to the centrifugal force, and this term is going to become 0 for a non-rotating blade. You have the inertia term, and then you have this extra term due to centrifugal force. So now we see that this term is going to create some difference in the formulation between the flap bending and the lag bending problem. So now let us think about the FEM formulation, and let us look at the kinetic energy term. So the kinetic energy term is going to be T is half integral 0 to L mv dot square dx, where I'm looking at a element of length L. Now if we use the same shape functions, and there is no reason to change the shape function here, we are still talking of a beam type of situation, we are going to get the same T, and we may end up with the same mass matrix. So that's something which is going to happen, is that since this term T is the same as the flap term, we are going to get the same mass matrix, at least in terms of the closed form expression for the mass matrix. Of course, the numbers will be different because the parameters may be different. Now let's look at the strain term. So the strain energy term is given by V. Now if you look at the first term here, that's the flexural energy component. You have a component due to T, and then you have this extra term which is the nu for the lag term. So this new term is going to reduce the frequency, and this is something which happens in lag bending. So the first two terms are very similar, or in fact same as those which are present in the flap problem, and therefore the equations or the type of expressions you are going to get for the corresponding stiffness matrix are going to be same. However, there is a new term here which is going to create a new component of the stiffness matrix. Remember that V is the source of the stiffness matrix. So if we look at this, what happens is that the stiffness matrix for the lag is the stiffness matrix for the flap minus mi rotation speed square into this 4x4 matrix here. And of course here we are presuming the same type of bending which we have obtained in the flap before. So essentially we have a 4 degree of freedom problem in the lag system. Now this matrix of course can be immediately calculated the moment we know L, and L is the length of the element you are dealing with. So you can very easily calculate that, but you need to keep in mind that this extra term is going to be present whenever we are calculating the stiffness matrix due to lag, and that's a difference between the flap and the lag problem. So finally, make some important conclusions here. Until now we have looked at all these motions as separate motions. We have looked at flap, lag, torsion as separate motions. But in reality these are not separate, they are united or coupled And the coupling is not something very simple or some second degree impact because of large deflections or something like that. In fact, it is happening because of the presence of Coriolis terms in the equation. And these Coriolis terms are sources of quite significant nonlinearity. So that is something to keep in mind. So in the next couple of lectures, we are going to look at the genesis of this Coriolis term, which comes in the flap lag equations, because of which these flap lag motions get coupled. And then we are going to explore the coupled flap lag equations. In fact, one of the reasons helicopter dynamics gets complicated is because of this coupling in the equations, which is present because of Coriolis terms. So very often a favorite question of people is, why is this helicopter system so nonlinear? And sometimes people say it's because of large deflection and so on. Now, large deflection is of course true, but the helicopter system is nonlinear primarily because of the presence of these Coriolis terms, and this is not necessary that the system must have large deflections for these terms to be present. These terms are present in general because of the rotation of the system. So it's a very fundamental fact that helicopter dynamics is nonlinear, and therefore all the equations, all the systems we look at are essentially nonlinear system, and therefore the solution process is quite complicated and time consuming. So I will stop this video here, and next class we are going to discuss the Coriolis forces. See you then.